Welcome, everyone. So, have you ever stood on a really crowded platform just watching train after train arrive with absolute clockwork precision and thought, how on earth is this actually possible? Well, today we're going to decode what I consider the ultimate transit puzzle. We're looking at that delicate, literally invisible balance between absolute railway safety and maximum line capacity. It's this completely fascinating world of physics, engineering, and AI working right beneath our feet. Just think about this for a second. How do you run 36 massive, high-speed trains an hour on a single track without a collision? I mean, that's barely over 90 seconds between each train. Solving this huge engineering challenge is exactly what we're going to explore in today's explainer. Okay, let's dive right into this. Here's our roadmap. 1. The capacity dilemma. 2. Fixed block train separation. 3. Moving block train separation. 4. Automating train operations. And finally, 5. Intelligent traffic management.
All right, kicking things off with Section 1, the capacity dilemma.
So, the absolute fundamental requirement of any railway is keeping people safe, right? Completing a movement with minimum risk. But alongside safety, we hit this capacity dilemma. How do we cram more trains onto the exact same amount of physical track? To really get this, we need to understand one crucial term, and that's headway. Headway is basically a measure of capacity. It's the minimum time or distance that's safely allowed between two following trains. Optimum efficiency, well, that relies on keeping this gap as unbelievably tight as possible. Any deviation at all from a perfectly uniform train movement increases that headway. And boom, you've just reduced the total number of trains you can run in an hour. Moving on to Section 2, fixed block train separation. So, how did early engineers actually keep trains from crashing into each other while managing this headway? Well, they used what's called a fixed block system, and this brilliantly illustrates the traditional approach. The track is literally divided into static physical sections, or blocks. The cardinal rule here is pretty simple. Only one train is allowed to occupy a block at any given time. The system uses continuous train detection, think track circuits, and it grants movement authority to the drivers via those classic colored line-side signals you've probably seen. But here's the catch. This method has a massive built-in bottleneck. Notice the minimum distance between those signals. It has to guarantee that there's always a full braking distance available. And because a line might host trains of all different sizes and weights, the system has to be designed around the absolute longest, worst-case scenario braking requirement. That means trains are often kept way further apart than strictly necessary, which, you guessed it, severely limits the overall capacity of the line. Which brings us to Section 3, moving block train separation. To fix the limits of those rigid physical sections, engineers made a massive technological leap to moving block systems. This is primarily done through communication-based train control, or CBTC. Let's look at these two side by side. With fixed block, the physical track dictates the spacing. Your safety margin is permanently fixed to the infrastructure. But with moving block, it's dynamic. The system relies on constant, real-time communication between the train and the control center. The train is always saying, hey, I'm exactly right here, allowing the system to calculate a dynamic safe zone on the fly. Suddenly, the track infrastructure isn't holding us back anymore. Now, what's really interesting about this slide is the visual proof of just how efficient this is. In the top example, you can see the fixed block forces the following train to stay an entire physical section behind, just wasted space. But look below. By calculating the exact braking distance based on the following train's current speed, the moving block drastically shrinks that required safe zone to a really tight footprint. This lets following trains safely bunch up, which is absolutely crucial when approaching a stationary train stopped at a platform. If this still feels a bit abstract, let's use a motorway analogy. When you're driving your car on the highway, the safe space between you and the car in front of you isn't some fixed section of the asphalt, right? Its length is determined by the distance you need to safely slam on the brakes from your current speed. As the car ahead moves, your safe space physically moves along with you. Moving block signaling gives massive trains this exact same fluid flexibility. And that brings us right back to this unbelievable number, 36. 36 trains per hour is the peak capacity achieved on London's Victoria Line. This massive uplift in service, going from 30 up to 36, was made possible solely by ripping out fixed line-side signals and transitioning to this continuous update CBTC moving block technology. It's a real game changer. All right, on to Section 4, automating train operations. Now, squeezing those safety margins closer together is really only half the battle. To run trains that tight, you need absolute unwavering consistency.
Modern rail relies on this alphabet soup of automation, which basically breaks down into 3 layers. First, automatic train protection, or ATP. This is your safety net. It rigidly enforces the speed limits. Then you have automatic train operation, ATO. This handles the actual driving, computing the absolute best speed and braking profiles. And finally, automatic route setting, ARS. This manages the workload, communicating with the electronic timetable to automatically set the track paths ahead of the train.
Let's move to the next visual and see how this all builds into an actual journey. Look at this graph. That red line? That's the maximum safe speed enforced by the ATP. But the blue line is where the magic, the efficiency, really lies. That's the ATO calculating the optimum, most energy-efficient speed curve. It targets the perfect braking profile, giving a flawlessly smooth and consistent ride that a human operator, honestly, despite their absolute best efforts, just cannot replicate perfectly every single time.
The compounding benefits of all this automation are just staggering. By stripping out human variability, we get those super tight headways needed for busy city metros. But we also gain massive energy efficiency. I mean, the computers can literally synchronize the acceleration of one train leaving a station with the braking of another train arriving, just to perfectly capture and reuse that recovered brake energy. How cool is that?
But it's super important to remember what this actually means for the humans involved. Automation doesn't just push human workers out, it elevates them. As this quote points out, by letting the IRSE handle the thousands of totally routine daily train movements, the operators in the control center are freed up. They can focus entirely on managing complex problem areas, talking with staff, and ensuring passenger safety. Which perfectly leads us into Section 5, Intelligent Traffic Management. All right, let's zoom way out. How do you manage thousands of automated decisions simultaneously across an entire city? Look at this incredible God view of a rail network. This is a traffic management train graph. The x-axis is time and the y-axis is physical distance along the route. Every single one of those angled lines is a train moving through time and space. That vertical violet bar, that is right now. Everything to the right of it is the AI's prediction of the future, which lets operators spot crossing lines, meaning potential conflicts, long before the trains ever even get near each other. So the crucial point here is that this isn't just about preventing crashes. It's about perfect fluidity. This platform Docker shows exactly which train is occupying which station platform, down to the second. If a train is running, say, 2 minutes late, the dynamic timetable recalculates instantly. It might slightly slow down a train following behind it or completely swap its platform assignment, all to ensure that one tiny delay doesn't snowball and cascade through the entire network. It honestly plays out like an incredibly complex, high-speed game of chess. The AI detects the timetable deviation, boom, it runs predictive conflict algorithms. Then, using connected driver's advisory systems, it subtly adjusts the speeds of trains miles and miles away. It might even tell a train to coast for a minute, rather than rushing up to a red signal and wasting energy, just so it arrives at a complex junction at the exact microsecond another train has cleared it. This is a total paradigm shift in transit capacity. Modern automated railways aren't reacting to delays in real time anymore. They are predicting conflicts and absorbing them into a dynamic, living timetable well in advance. The system dynamically heals itself before you or I, the passengers, ever even notice a disruption.
Which leaves us with a pretty fascinating thought to wrap up on. As moving blocks tighten our headways, and AI seamlessly predicts and avoids conflicts, are we moving toward a future where the concept of a rigid, printed train schedule disappears entirely? Could it be replaced by a constantly flowing, living system that just continuously adapts to the city it serves? It's an incredible, invisible world keeping us moving right beneath our feet. Thanks so much for joining me on this explainer, and keep your curiosity on track.